So good morning and welcome to another talk of the spring edition of Chemforum. Today we have the pleasure of having Isabel Marrucho. She's one of the new CKA members since she joined the Chemical Engineering Department as an associate professor this month. So congratulations and welcome to CKA. She graduated in '89 in Chemical Engineering here in Technico and did her PhD also in Chemical Engineering from Technico and the Colorado School of Mines in the United States. From December 97 to 2013, she was an assistant professor at Universidade de Aveiro. From September 2008 to 2013, she was an assistant researcher at Instituto de Tecnologia Química e Biológica within Ciência 2007 program. And from September 2013, she was a researcher coordinator also at ITQB within the Investigador FCT program. Isabel's current interests focus on green chemistry and alternative solvents, in particular Ionic Liquid-based materials. So I think she's going to give us an overview of her research. So welcome.
Thank you all for being here. It's a great joy for me to be here because, in fact, I am, as Christina said, I'm a daughter of CKE, and so it's a great pleasure to be back here again. And Christina was right. I'm going to take this opportunity to make a brief overview of what I've been doing and what my group does. So we are called the Separation and Extraction Technologies Group, and we are a group of chemical engineers, chemistry, and material science majors. And the aim of our research is to develop more efficient and sustainable processes and products. But we always use a top-down approach, meaning that we are motivated by the general, by the application, but our research also encompasses fundamental studies. The way that I perspective my group is that we have two main parts, one that deals with the separation from the liquid state, and the other that deals with the separation from the gas state. And what unites us together, it's the use of ionic liquid-based materials that I will talk briefly in a little while. So who are we? The people that do the separation from the liquid state, my PhD students are listed here, and they basically use liquid-liquid extraction or adsorption techniques to remove, let me see if I can work this, to either remove pollutants from ecostreams, and we use the same techniques for virus purification and concentration of the diagnosed compounds. And right now, we are also developing some sustainable strategies for biorefinery separation processes. Regarding the gas state, we have been developing membranes based on ionic liquids and polymeric ionic liquids. And right now, we are very much interested in high-temperature materials. And so we have been developing high-temperature materials for membrane gas separation and also as sortive phases for chromatography. The other people that work with me are people that really work on material science. So they develop materials with a specific purpose. They incorporate ionic liquids with a point of view, so to enhance the performance of these materials. For example, Nuno, what he does is he uses ionic liquids to fibrillate proteins, and so to create better materials with more mechanical properties. Okay. So I've been talking about ionic liquid-based materials, and I divided the ionic liquid-based materials in three parts. One of them is solvents and materials. I really don't know if I need to talk about ionic liquids for this audience. Ionic liquids are very well known for their properties, for the set of the properties that they have. But what thrills me more about ionic liquid is the tunability of the properties, so that I can tune the properties and develop solvation schemes to enhance my separation processes. Very recently, we also became very interested in eutectic solvents. Eutectic solvents have everything that green solvents should have, or sustainable solvents should have. They are made from natural products, so they are sustainable, they are easy to prepare, they're cheap, they are low toxicity and biodegradability. And what I like them very much also for is because they have properties that are similar to ionic liquids, meaning that I can have some sort of cousins of ionic liquids, but they are greener than ionic liquids. Then, within our applications, we felt the need of having solid state, ionic liquids in the solid state. We did not want ionic liquids to drip. We want to be able to hold the ionic liquids. And so we started to develop polymeric ionic liquids. The idea of developing polymeric ionic liquids is to have materials that have the same properties of ionic liquids, but, so they are tunable and all that, but they have also the mechanical properties of polymers and the architectural features of polymers. And that is going to be very nice for some of our applications. Okay, so now here, not to bother you very much with my research, I picked up 4 what I can consider typical examples or what I do. So the first 2 deal with the liquid state, and the last 2 deal with the gas state. So here I'm going to talk a little bit about aqueous biphasic systems for pharmaceuticals removal, deep eutectic solvents as tailored solvents, peels as sortive phases for chromatography, and composite membranes for CO2 separation. Okay, and I'll start by aqueous biphasic systems for pharmaceutical removal. Just give me a minute. We all know what emerging contaminants are. We all know that they are chemical or natural substance that have been entering our aqueous streams. Probably they have been there for a very long time in very low concentrations, but the improvement of the detection limits of most of the analytical techniques made us know that they are there and they are harmful. And there are a lot of legislation that has been coming out about extracting all these pollutants from the aqueous streams. The problem is the wastewater treatment plants, they do not have special separation modules to separate these pollutants. And so there is the need to develop efficient separation techniques for these emerging contaminants. These emerging contaminants are mainly pharmaceuticals, pesticides, cleaning agents, and specialty products from specific industries. And today I'm going to focus about the pharmaceutical products. This is such a big issue that several of priority lists have been put forward so that some of these compounds need to be banned up to 2020. The idea is that we should develop specific techniques to remove from water streams these compounds. And we are going to focus here on the non-steroid anti-inflammatory drugs, and we are also going to focus here on fluoroquinolones as an example of synthetic antibiotics. We picked up fluoroquinolones because we've been working with fluoroquinolones for a very long time due to a collaboration that we have with Bayer. The way that we try to approach this is using aqueous biphasic systems. Aqueous biphasic systems have 2 aqueous-rich phases in equilibrium, and they have been known for a long time. But only in 2003, Robin Rogers introduced the ionic liquid aqueous biphasic systems concept. More recently, I have been involved in some studies unveiling aqueous biphasic systems using ionic liquids and polymers, sugars, amino acids, and other salting out agents. And thus it seemed a good idea to use this technique to extract the proposed pharmaceuticals from aqueous streams. What do these systems, ionic liquid-based aqueous biphasic systems, have that the other ones do not have? Because they use ionic liquids, they have a high tunability of their phases. So there are so many ionic liquids that I can choose an ionic liquid that I can carefully tune, and here is polarity that is important. The polarity of the phase so that I can achieve a high extraction efficiency. When we thought about this, we thought, now we're going to introduce an ionic liquid in water, then we are going to introduce a salt. So we minimize the amount of new compounds that we are going to put in there. And so we researched and found out that aluminium sulfate is already used as a coagulation agent in wastewater treatment plants. And so we implemented aqueous biphasic systems that have this salt and ionic liquids. Unfortunately, not very many ionic liquids make aqueous biphasic systems with this salt. Envisaging also sustainability, we tried to implement, I wish I could work with this. We also tried to implement aqueous biphasic systems with citrate, because citrate is biodegradable, and this would be a great help in the end. So using these aqueous biphasic systems, I can show you what we did. These are the ionic liquids that we used, and what we can see here is for the NSAIDs with the two salts, it seems that the pH does not really matter. The use of aluminum sulfate salt puts the pH around 3-4 acidic, and the use of citrate salt puts the pH around 8-9, so basic pH. But in all of these experiments, we were able to achieve extraction efficiencies around 99-98%. Regarding the fluoroquinolones, the same is true, although here a lower extraction efficiency around 95 was obtained, and here 99% was obtained. This is an extraction in one single step, so I think that these are very nice results. Now, all the questions that everybody asks us. How can we do this? Ionic liquids are so expensive, and you're throwing a huge amount of money down the drain to take out pharmaceutical compounds. That is true. So what can we do to improve our process? The way that we can improve our process is by minimizing the use of the ionic liquid. So here I have the aqueous biphasic systems. Here are the two phases region, and here is the one phase region. And I'm walking along the largest tie line, which guarantees me a very different composition between the two phases in equilibrium, and thus most probably a better extraction efficiency. And I could concentrate up to 13 times my pharmaceutical compounds in ionic liquids. This is for NSAID diclofenac. What about the extraction efficiency? So I concentrate it, but can I extract it also? Here is the extraction efficiency. We can see that by concentrating the compounds in the ionic liquid, I can achieve a higher extraction efficiency. And the same holds for ciprofloxacin, one of the fluoroquinolones that we've been using. We could concentrate it and also maintain or upgrading the extraction efficiency. Okay, a really good thing, now that I concentrate them, would be to recycle the ionic liquid phases. Ionic liquids are expensive. I need to remove the compounds from the ionic liquid. I cannot afford to throw the ionic liquid away. And with this idea in mind, we tried to develop, we separate the ionic liquid rich phase with the active pharmaceutical ingredients, and we use two different techniques to precipitate the APIs from the ionic liquid rich phase so that we could recycle it. The strategies were very simple, in fact. In one of them, we just added a little water, and as NSAIDs have very little water solubility, we were able to precipitate them. And with fluoroquinolones, we just use a salt to put the pH equals to 7, which is where fluoroquinolones are neutral, and they precipitate also. So as you can see, I hope that I could show you that aqueous biphasic systems are a good strategy for pharmaceutical removal, that we can design them to have a high extraction efficiency. I can design them to concentrate, not also to remove, but to concentrate, and to recycle this ionic liquid phase. The second example that I'm going to show you talks about eutectic solvents. We have been very much interested in deep eutectic solvents because of the sustainability, green chemistry, green chemical engineering. Those are topics that we really would like to work in, and we are very interested in working because we think that they will make the difference. In fact, when we search the literature for deep eutectic solvents, we can see that there is a lot of articles related to dissolution of biomass into these ionic liquids, but very little is known about their thermophysical properties. And for us, as chemical engineers, it is very important for us to know the thermophysical properties before we jump in a separation process. We know that the worst property of the ionic liquids, I've never said this, is the high viscosity of some ionic liquids. And these deep eutectic solvents, we were afraid that were going to be very viscous also. And so what we did, it was we choose selenium chloride as the hydrogen bond acceptor and a bunch of organic acids as hydrogen bond donors, and we prepared deep eutectic solvents. We prepare deep eutectic solvents just like the literature tells you. You just put the two solids together and you heat them up. And we usually, after we prepare the ionic liquids or the deep eutectic solvents, we run an NMR. And what we found out is that we had an impurity. And this is very unusual because the eutectic solvents are known to be great because I just put 1 and 2 together. There are no side products. I don't have to purify them. They're great. But in fact, what we found out is that we had an impurity here. And we went back again to the literature, and some other authors also mentioned this peak, but they never present any explanation. So we were able to use MALDI-TOF and to come up with an explanation for this impurity. It seems that the cation from the selenium chloride reacts with the acid and forms an impurity. And so we were talking about this with one of our friends, Robin Rogers, and he suggested using the grinding method because he had been doing it for double salts also, and it worked really nicely. And when we used it, it worked very nicely for us also. So no impurities are contained in this gas prepared by the grinding method. So we really adopted this method for eutectic solvents done with acids. So now we want to compare the properties of deep eutectic solvents versus the selenium analogs. What does this mean? For instance, I have the ionic liquid selenium melanate, and I want to compare with the deep eutectic solvent that has selenium chloride and malonic acid. In terms of densities, what we can see here is that the deep eutectic solvents are typically denser than the ionic liquids. However, when we come to viscosity, it is very good to know that these ionic liquids are much more viscous than their corresponding deep eutectic solvents. And this is very nice to work with deep eutectic solvents because they are much less viscous than the ionic liquids, especially at low temperatures. So what can we do this? We are an extraction group, right? And so we went ahead and we picked up one of the hot themes in the literature of ionic liquids, which is azeotrope breaking. And we tested the developed deep eutectic solvents in azeotropic breaking of ethane and ethanol. And here are the results that we obtained, because our aim was to compare with the literature. So we built up the phase diagrams, the ternary phase diagrams for 3 deep eutectic solvents, always with selenium chloride, with glycerol and levulinic acid and ethylene glycol. And here are the results in terms of distribution coefficient and selectivity. When we compare with the current state of the art for ionic liquids, we can see that we are doing much better in both of these parameters, indicating that deep eutectic solvents are really promising in this area also. Again, we developed a recycling strategy that was very helpful because we were able to recycle the deep eutectic solvent by slowly evaporating the ethanol. I know that slowly evaporating the ethanol is not the most sustainable thing, but we could not do anything else. The good news is that the deep eutectic solvents do not break apart. So I don't have any selenium chloride alone or any acid alone. We are able to verify that using NMR. Another idea that we have is that most of the deep eutectic solvents are very hydrophilic. They are powder, but if you leave them and go and have hot coffee, when you come back, you have a liquid. And so what we thought it would be very nice to have an hydrophobic deep eutectic solvent. And we searched for salts that would be hydrophobic, but that's very difficult to have salts that are hydrophobic and at the same time come from renewable resources. And so we ended up developing this eutectic solvent that is not based on a salt, I have to remark this, it is based on menthol, on a neutral compound. But it can make very nice hydrophobic deep eutectic solvents that separate with water. What is more, if you don't remember, so this here go up to 12,000 millipascals per second in viscosity, and this one here, this scale here goes up to 400. So the viscosity difference is huge. These things are very easy to manipulate. They are very nice. The extraction is performed very quickly because they have low viscosity. Here I also have to mention the quantities of water. Saturated eutectic solvent with menthol has less than 1.5%, and the saturated eutectic mixture with colinium chloride has 15 to 18 weight percent in water. Okay. At the same time that we proposed this, somebody else also proposed hydrophobic deep eutectic solvents based on ammonium with long alkyl chains. And so we decided to use this ammonium with long alkyl chains again to do azeotrope breaking, liquid-liquid extraction for azeotrope breaking, this time using aromatic aliphatic extractions. This is a work that has been going on, and we are using the NMR as the analytical technique, the NMR using a capillary tube so that we don't have solvent inside. Okay, so these are the things that we've been developing with deep eutectic solvents. Those are, I think, are two illustrative examples of the extractions from the liquid state. And now I'm just going to focus a little bit on the extractions from the gas phase. In fact, this first example that I'm going to talk about is really still, the way that I'm going to present it to you is still a little bit conceptual, although we've gone far beyond of what I'm going to show you. So what we were trying to do is to develop we were trying to play around with SPME. And SPME is solid phase microextraction, is a technique that is used to concentrate compounds, to concentrate solids. It is very nice because it doesn't we don't have to use solvents. It just relies on this coating here on top of this fiber. And so we put this coating in contact with the headspace of our sample, and we absorb the analytes from the headspace of our sample. We take it out, we put it inside of the GC injector, and we desorb our compounds, and they are going to be detected. So this is truly a very valuable technique, even when there's only 3 available commercial fibers. Okay, so what this means is that if we want to go further beyond this technique, we need to develop, or it would be very nice to develop, things that would be specific for targeted compounds. And this really rings a bell. It really sounds like ionic liquids. And this was proposed in 2008 by Anderson. Anderson used polymeric ionic liquids, and he coated one of these fibers, and he found out that he had a higher sensitivity and a lower detection limit, and he was working with esters, and he have selectivity in the polyionic liquids that he was developing. So our contribution to this field is, where am I? Our contribution to this field is we are also going to use polymeric ionic liquids, but we are going to use UV polymerization. UV polymerization is very nice because we have here the solution of the monomer, and the cross-linker agent. We just dip our fiber in it, we put it for a couple of seconds under UV light, and our coating is done. And here we have to be particularly careful because we are going to put this in the oven of the GC, in the injector of the GC that is at very high temperatures. And we've developed some polymers that can take up to 300 degrees C without melting, because it is important that they do not melt. What is more, by using a cross-linker, we created a porous matrix, so we enhanced the surface area of contact, and we can sample quicker our sample because we have a higher surface area. What are we aiming to do with this? Basically, what we wanted to do is to do breath analysis. Breath analysis is an extremely fashionable subject, and we all know it from the ethanol, from the driving laws. Everybody has already been stopped and asked to blow inside of the machine. But there are other analytes that are able to indicate if you have certain diseases or not. For example, it is very well known that if you have acetone in your breath, you have diabetes. It has also been used, the branched hydrocarbons, it's been used as a detector of heart transplant rejection. Nitric oxide, it is known as asthma. And so what we wanted to do with this, it was to develop a breath analysis to detect lung cancer biomarkers. So we've been working with the Instituto Português de Oncologia, and they've been telling us which biomarkers we need to tune our polymers for. And so we've been trying to do this breath analysis with them. And this is where we want to go. Okay, so now I come to the last part of my talk. Where I'm going to show you some results that we've been doing for quite some time on the preparation of composite membranes for CO2 separation. We've been working on this theme for like 5 years, and we've recently published a paper, a review paper, where we made an highlight on ionic liquid-based materials and how they can be used to prepare membranes for CO2 separations. In this publication, we covered the 4 different membrane configurations. But here today, I'm only going to talk about this one here that involves polymeric ionic liquids. Of course, that ionic liquids have been used for a long, long time as absorbers for CO2. And so there is much more work done on ionic liquids than on polymeric ionic liquids for CO2. And in fact, we also started using supported ionic liquid membranes for CO2 separation. When we changed from here to here, what happened was that our permeability greatly decreased. And we were also not able, greatly decreased. And this is probably because we have here a liquid state and here we have a solid state. Another thing that we verified, here we have liquid inside of a membrane and it was coming out when we pushed it with pressure of the gas. And we wanted that not to happen here. But when we fabricated these membranes just with polymer, they were very breakable. They were very fragile and they break. And so what we decided to do, and what everybody does in the literature, is to blend ionic liquids with polymeric ionic liquids. And this gives us not only a liquid-like state in our membrane that helps our gas to diffuse faster, but it also enhances the mechanical properties of our polymer. And so we are able to have membranes that are more feasible for commercial use than what we were having just with polymeric ionic liquids. Probably, as you all know, my background is thermodynamics and physical chemistry, and so I'm completely hooked on going from ionic liquids to polymeric ionic liquids and trying to translate what I know from ionic liquids to polymeric ionic liquids. And so what we've realized when we came to this field is that most of the work that was done, it was on imidazoliums, and most of the work, I would say 99%, was on imidazoliums, and nobody had ever searched the most important cations in the ionic liquid chemistry. And so that motivated us to produce polycations to produce polycations that were prepared with imidazolium, pyridinium, pyrrolidinium, ammonium, and collinium cations. We combined these with NTF2, they are always combined with NTF2, and we had to insert a little bit of ionic liquid inside of all them to plasticize and to make permeability larger. Realize that the ionic liquid that I have to put inside of the polymer matrix, the membrane, has to be compatible with the polymer, otherwise it segregates. And so I would like to show you here some results. And this is, we could confirm that the permeability of the gases, let me explain a little bit more this. So we did permeability of CO2, methane, and nitrogen. Right? Yes, methane and nitrogen. These things are very small. I should have put this larger, I'm sorry. Carbon dioxide, methane, and nitrogen. And what we can see is that for all the gases, the permeability is related to the diffusivity. And this is new, but it's good that we can confirm this. We also verified that the collinium bases were the ones that have the lowest gas permeabilities and also the lowest gas diffusivities, while the pyridinium were the ones that have the highest gas permeabilities and diffusivities. So it is really interesting that the most used polymers are not the most performant polymers. And what we did is that we did not choose either the imidazolium or the other one, the pyridinium. We choose pyrrolidinium. And why did we choose pyrrolidinium? We chose pyrrolidinium because we verified that keeping the molecular weight was very important for our membranes. And pyrrolidinium is commercially available. We can buy this polymer, and we can just do an anion exchange reaction and get our polymeric ionic liquid with the NTF2 anion. In this way, I know that I have always the same molecular weight, and this is a very straightforward strategy because this is already available. I don't have to go into purification steps. I don't have to worry about the molecular weight and characterizing the polymer because the supplier helps me in doing it. Okay, so we are going to do pyrrolidinium polymeric ionic liquids. Now, another thing that we thought it would be very interesting is it linear? How much ionic liquid can I add to the polymer? Can I add up to 100%? Can I go from pure ill to pure pill? And so what we did is we did a couple of membranes. We prepared a couple of membranes with the increasing concentration of ionic liquid. Realized that we were able to fabricate membranes with 80% of ionic liquid, but these membranes were not stable anymore. They were gel-like, and so we had to support them, as well as the pure ionic liquid. So these two are supported ionic liquid membranes. These are supported ionic liquid membrane. This is just a supported membrane with the composite, and the other ones are membranes that we fabricate by solvent casting, and they are very nice. Now a little bit of the results. So the results are what we thought they should be. The pure pill has the lowest permeability, the pure ill has the highest permeability. The permeability and the diffusivity are correlated, as we saw before. And we could also see that the enhancement, And we could also see that the enhancement of the ionic liquid content increases either the permeability and the diffusivity. And so it is very important, as you can see, to attain a high gas permeability, we need to have a certain amount of ionic liquid inside of the polymer. Ionic liquid mixtures are very fashionable nowadays, and we know that we can tune properties with ionic liquid mixtures. So the question is, can I prepare polymeric ionic liquid mixtures, or in polymer chemistry words, can I prepare random copolymers with different anions? Yes, we were able to prepare pyrrolidinium copolymers with 50-50 of different anions. These anions have always to be hydrophobic because we use an anion exchange reaction and they have to be miscible with water. But we were able to prepare a variety of polymers with different anions. Now the idea is, does this make a difference when I do gas separation? Yes, we can see that here it really makes a difference. Look at this. Look at this permeability for CO2. These are the permeability for the different polymers that we prepared. So we can see here, then when we exchange in NTF2, when we introduce the dodecyl sulfate, what happens is that I have an increase in permeability. On the other hand, what happens with the other anions that I've used is that they decrease the permeability. And this happens for CO2, and it happens for methane, and it happens for nitrogen also. So this means that exchanging the anions is a good, straightforward way to tune the properties of my polymers. Very recently, we came across the cyano-based anions. Cyano-based anions are very nice, and they have been used quite often in ionic liquid chemistry, and so we thought about preparing polymeric ionic liquids with cyanoanions. Everybody knows that the ionic liquids with cyanoanions absorb a lot of CO2, absorb a lot of CO2, and we were wanting to see what happens when we prepare polymeric ionic liquids with these anions. So we tried a variety of anions. We used dicyanoimide, we used tricyanomethane, and we used tetracyanoborate. The thing is that, so we prepared the polymers, and then we cast membranes with 20, 40, and 60% of the same ionic liquid. The very interesting thing is that the membranes were not stable at all, even though we could think that the ionic liquid would be compatible with the polymer because they are very similar to the monomer, but in fact they segregate, they break, they form gels, and so these are very difficult to prepare. Here in the tetracyanoborate, they are all segregated. However, when we put results together of the ones that are good, the results are very nice. And I'm going to give you an overview now of what I've been talking about. So this here is the Robson plot. And the Robson plot plots the permeability of the most permeable gas divided by the permeability of the less permeable gas, so the perm selectivity, against the permeability of the most permeable gas. This has been proposed in 2008 by Robson and this line. And what this line means is that Robson just collected a huge amount of data for CO2 and N2 separation from commercial polymers, and he just drew this line. So this line indicates what we have, the state of the art that is commercially available. So everything that goes above this line is an improvement over the current state of the art. The open symbols that we have here are data from the other authors and sometimes ionic liquids also, and the colored symbols are data from our work. We start by the purple ones, and the purple ones indicate the polymeric ionic liquids that we developed with different polycations. We can see that they are all here in this region. We can see that they have very low permeabilities, but they maintain more or less the same perm selectivity. However, when we introduce the second counteranion, what it happens is that I get a broader range of permeabilities. So now I can tune the permeability better, but the perm selectivity still stays more or less the same. Okay, the green symbols, they represent what we've done from eel to pill. This is the pure pill, and this is the pure ionic liquid. And so we can see that truly what really tailors the permeability, it's not the change of the polycation, it's not the change of the anions, but really the introduction of ionic liquid inside of the polymer. Now, these are the data that I wanted to show you also on the cyano-based anions. we are very excited with this data because, as you can see, these polymers are really tunable. And they are not only tunable, but they surpass what is the presently known as the current state of the art. So here we have prepared this composite of 3-cyanomethane with 60% of ionic liquid. And we can see that here we not only increase the permeability, but we also increase the perm selectivity. And so these anions are really very promising for CO2 separation. And this is what we have been doing. We wanted to put everything else above the line. There are other results here that I did not mention in this presentation. Where am I? There are the results here that I did not mention in this presentation. And these are also other cyano-based anions of an ongoing work in our lab. Okay, so I think that I could convince you that ionic liquid-based materials are really tunable platforms, and we can use them either in the solid or the liquid form to develop separation techniques. We just need to use our imagination because there are a huge array of cations and anions that are available and that we can play with. Now I would like to acknowledge all my co-workers. I think that here from ISTs and Nuno Canongia Lopes has been the person that I've been working the most with. And thank you all for your attention.
Thank you very much for this nice overview of your research, which is now open for questions.
Hi. Very nice talk. Just a quick question. You obviously only gave us some examples, but concerning the membranes, did you try to correlate? You concentrated on composition. I understand, but did you try to correlate the measurements with the structural characteristics of the membrane in other techniques? Because very often that's what matters, not the composition or the structure of the membrane, which is related to composition, obviously.
You're trying to ask me if I can understand what happens when I change from imidazolium to pyrrolidinium and collinium and stuff like that.
And how it affects.
We tried, and in fact it is possible, but mostly what you can see here is the effect of the ionic liquid opening up the chains. Okay, because when you're interested in when I work just with the polycations, is that what we?
All of them.
Because just with the polycation, it's really how the chains pack. And sometimes how like for instance, imidazolium, it's aromatic, and so it packs more. You can see that pyrrolidinium, which is the one that we worked with, it has the charge on the backbone, and the other ones have the charge hanging from the backbone. That matters also. For instance, what I haven't told you. What I haven't told you, for instance, is that most of the work that has been done with imidazolium, they use a cross-linker in order to prepare their membranes. And this here, we have no cross-linker. So we just prepare them by bulk free radical polymerization. And so it's very difficult to compare and to reason out because in terms of polymers, I think that each people uses their method to measure, and each person uses their way to prepare the membranes.
Yeah, but I was talking about characterizing the membrane, the structure of the membrane with some other physical technique. For example, we've been measuring gas permeability and compare with positron and
Iniculation.
measurements to understand how is the structure of
No. What we've been doing that I did not show is mechanical tests. We've been doing mechanical tests to see how fragile they are. But we have never studied the membrane per se. No, we tried to do also some experiments with water. But these membranes, the way that we prepare them, they are not good to use with water because they swell. They swell. And so, but if we use a cross-linker, we can diminish the swell, and so they are good to use in water separation. But we've never tried to correlate or the surface properties or contact angles. No, we've never done it. No. Hydrophobicity, we don't know what stands up, if it's the N2, if it's the CH3. No, we don't know. If you want to do it, we can collaborate.
Any more questions?
Isabel, what about porosity?
Okay, that's a good question. Our membranes, the membranes that we fabricate are dense membranes. They have no pores. And our idea was, because if you have porous, you sieve through size. If you have a dense membrane, you sieve through solubility. And so we thought that since we have what we can grasp or what we can control is the solubility by changing ionic liquids, that we would start with dense membranes, because the material per se would sieve the gas. Right now, we are very willing to start preparing porous membranes, yes. And I think that we are going to prepare porous membranes. To take some advantage of these materials as porous, we have to go into that area that we have to have tight porous, so that we don't sieve only through the size of the pore, but the molecule contacts with the pore walls so that it's sieved also through solubility. Okay, so we don't use an ionic liquid material just like any other material to prepare pores, but we also take advantage of the solubility selectivity that our polymeric ionic liquids have.
Any more questions?
Okay, yeah, I was interested about this biomarker, the stuff that you do in Shapiro.
Mm-hmm.
So this is basically cat space capture from exhale specimens.
Yes.
What kind of molecules are you looking for? You know what you're looking for?
Yeah. We are not proposing biomarkers. We are not at that point. So what we are trying to do is we are trying to design polymers that specifically sorb specific groups of molecules. So we've been working on alkanes, ketones, aldehydes. So we've been working on several families of compounds and trying to design and to introduce functional groups in the polymer to enhance the sorption of those molecules.
And then you characterize by GC?
Yes.
Against
Yes. What we've been doing so far is GC, but we are also going to do GCMS and other hyphenated techniques, yes.
Because if you want to do like a metabolomics analysis,
Yeah.
you would definitely need to do that with GCMS.
Yeah. So right now we are on the GC because we know very well what we have. We have standards inside of our samples. Once we pass through to natural samples, we have to go to GCMS.
Then the actual patient samples.
Yet, no. We've done one which was with urine, so it was not exhaled breath, it was with urine, and it was quite a mess. It was quite a mess. So first we evolved into that way, and then we said, no, there's no way that we're going to go there by just starting with the samples from the patients. We have to step back, tailor to specific molecules, and then go. So David, he is the one who is doing his PhD on that. He still has 2 more years to go. So.
Because the matrix can be very complex, of course. Because there's a lot of approaches. I mean, I've been reading some other, people take it in nasty stuff. Because one thing that's very interesting is that, for instance, if dogs can definitely identify colon cancer patients.
I'm sorry?
Dogs.
Oh, dogs. Yes. In fact, what they've done once in IPO is they used rats. And they say that rats, they have 99.9% confidence.
Are absolutely amazing. They can smell
And
and they identify
and so
very positive.
and so the idea would be,
Has to be
to cross those. In fact, they told me when I went there that they did like with patients and people that worked in the IPO, and they set them all on a class. And only one rat was mistaken that identified a person that did not have cancer. And the rat said that it had cancer. Now they are following that person to see if he is going to develop cancer, and the rat smells something that...
That's very interesting, because I think there's a lot of potential there as far as identifying profiles of metabolites that actually could be very early biomarkers.
Yeah. So to cross these two things is interesting, yes.
Any more questions?
Pode ser, sim. Dá dinheiro. Dá dinheiro.
Okay, so another question.
Nice presentation, and welcome to the department.
Thank you, Henrique.
Just a question about the last example you showed about the CO2 separations. Is this already the time to compare with other techniques in terms of efficiency, in terms of costs? I mean, for application, industrial application?
Yes, probably it's coming to a time, yes. We would like very much to do so. In fact, there is nothing done. In this review that we published, in the last section, we do a small discussion on that and how it hasn't been done, nothing has been evaluated in the whole process, the process as a whole. So how many steps, what would be the modules that we would propose? Nothing is done yet. No, we are still working on these flat sheet membranes. Not only us, but the other people are also still working on the flat sheet membranes, yes. Yeah, there is still a long way. There's been some work done with contactors, but not in the way that we have been doing it now. So they are slowly evolving to contactors now.
Okay, so let's thank Isabel once again.
Thank you.